Okay, let's continue with chapter number 2 of our program. In this chapter, we will talk about mechanical actions and the equilibrium of non-deformable bodies. So mechanical actions, that means forces, movement, or torque. So this part is very important for you because understanding this chapter is definitely necessary for you to be able to understand the rest of this program. Okay, so we'll try to cover a lot of definitions here that will allow you to understand the rest of this program. So this is the content of this chapter. We have 4 points: introduction, mechanical action, and isolation and equilibrium of solid. And at the end, we will try to solve some statics problem. That means some exercises. Okay, so this video will try to cover the two first point. It means introduction and mechanical actions. Okay, mechanical actions means just like forces we see every day around us in our daily life, and we'll try to define them and try to represent them, how to represent force in a problem, civil engineering problems. So the introduction is not that long, just 2 sentences. So statics is studying mechanical action that apply on non-deformable body in equilibrium. So because this program is about statics, so you need to understand what is mechanical, what is an mechanical action, because statics is considering the effect of this mechanical action on non-deformable body that are in equilibrium. Okay, so in this chapter, we will try to materialize the mechanical action that is acting on solid element, solid body. Okay, how to make the symbol of this, how to model these mechanical actions. And secondly, we will try to study the equilibrium condition of these mechanical actions on the bodies, considering the statics, the hypothesis of statics we introduced last time. So you need to know first what are mechanical actions, define them, and know how to represent them in any statics problem. And secondly, we'll try to study equilibrium of this equilibrium condition of the non-deformable bodies in statics. So this video will cover this first point, this first objective. You will know at the end of this video what are different type of mechanical actions and how to represent them. Okay. So this is the core of this chapter, of this video, mechanical actions. Okay. So definition. So generally speaking, we call mechanical action any physical force, physical element likely to maintain a body at rest. This is just, I don't want to say action or force, like physical action, mechanical action, physical cause that likely maintain a body at rest or create, maintain, or modify a movement. Okay, so Another definition is a physical cause that can deform a body. All these you may already know what mechanical action means. It means maybe force or moment or torque, these kind of actions. Okay, so mechanical action which are applied on solid can be divided in two large families. Okay, two large big families. Okay, the first one is forces, family of forces. This means pushing or pulling along an axis, and representation is something like that. This is first big family. Second big family are moment. The moment like rotation or twitching around an axis. That is moment. Okay, so we will try to see some example, few example in each family. This is very elementary, and you need to understand this part before to be able to understand the rest of this program. Okay, so some example, we will take the first family of action, mechanical action, forces, pushing or pulling around along an axis. So representation will be like this. One example is when you are pushing a car, for example. This is a car, and maybe you want someone to push your car to be able to start your car, to start the engine. So when you are pushing this person is pushing the car, and what is the car going through? This force will be acting on the car, the force that this person is pushing, using to push the car. Okay, and at the same time, what you are feeling yourself, you will feel the same force, intensity of force, but in the opposite way. You see, this one is minus F, this one is F. Okay, which will the reaction of the car on you. You will feel in your arms that something is, it's like you are pushing yourself. Okay, this is just one example for example number one. Example number two, we have support. In case you support an object, you put an object in your hand like this, and due to the weight of this object, you will feel the weight, right? At the same time, your hand is maintaining the object. Okay, so what the object is subjected to is this force, which is just the reaction of your hand. And what your hand will feel is the weight, okay, the weight of this object. Okay. All these kind of uh, example are physical, mechanical actions. Okay, so mechanical action, the first big family, forces. This is example number two. And let's go now for a moment, the second big family of mechanical actions. Moment, which means rotate or twist around an axis. So one example, the representation is something like this. So the force, and you did this. M is for moment. First example, rotating a door around its axis. When you open or you close a door, the force you are using, the force is rotating around its axis, right? So the force is, the door is like this. This is where you grab and push or pull, okay? When you are pushing or pulling this at this point, the force is rotating around its axis, this axis, right? So the rotation around this axis, the force you are using to open or close the door is causing a moment around this axis, right? So you are applying a force from offset from the axis, okay, not directed toward this axis, not this direction. Okay, the force is far from this axis. Okay, here, so you will have a distance between the axis of rotation and the axis of your force, or direction of the force you are applying. Okay, this is the direction of the force you are applying, like this, right? And this is causing a moment. Okay, this causes a moment of this force around this axis, the axis of this door, like this. So this means the moment is caused by a force, right? So this is the moment around this axis caused by this force, right? So the moment will be mf. This y should not be there. It means the force, the intensity of the force that you multiply by d. Okay, m, the moment is, the unit is in Newton meter, and f is in Newton, not, and d is in meters, in meter. So d, what is d? If you take this door, I will fix this soon. Okay, if you take this door like this, if you are seeing the door from the above, from the top, so this is the wall, and this is another part of the wall. So the door is rotating here around this axis. So depending how you apply, what is the direction of your force, the force you are applying, you will have different value of d, because d is just the distance between the rotation axis and the force you are applying. And that distance is just the perpendicular, the shortest distance between these two axes. So supposing you apply and the direction of your force is this direction, and the axis of the rotation is here, right? So the distance d will be this. As you can see, this distance is perpendicular to the force you are applying. This d is this value. And if you change the direction of your force like this, you see, d is changing. You change again in this direction, you can see here, d is 0. In that case, this force doesn't cause any moment around this axis. All right? Okay, let me fix just this and we continue, okay? Here, we don't have this. This is just F of this force, the moment of this force. Okay. And this is just in Newton. The force is in Newton. Yeah. So this is example number 1. Okay. Rotating a door around its axis. Example of a moment. Example number 2, turning a wheel like this. When you have this kind of tool and you want to, for example, this, in this case, where is the rotation axis? The rotation axis is this axis, y axis, right? And the force is here. Okay, so you apply the force here and try to turn this here. And the distance at that time, the distance between the axis of the rotation F and the axis of rotation and the force axis of the force is this distance. Okay, so you will have, in this case, you cause a moment of the force relative to the axis of the rotation. So in the example number 3, it's same case. Okay, in the case of wheel, same case, but in this case, you are using two forces. This force and this force. It's like this. You are rotating at the same time, right? So this rotation, each force has its distance between the force and the rotation axis. The rotation axis is this force distance is L, and this one is distance is L. And if you can see here that these forces are opposite. Then the sum of these forces is 0 because they are opposite. Okay. However, these two forces generate a moment around this rotation axis, right? So the mechanical action in here by this key on the wheel is called a torque. Okay, we will talk about a torque here instead of a moment. Torque, right? Because you can see here rotating or twitching around axis. Example number 4. Here, when you want to adjust, for example, the volume of radio or something, or adjustment button, you rotate like this, okay? Which means you apply, in this case, in this axis, there is no force at all, okay? You exert a mechanical action involving no force, but only twitching, okay? You twitch like this. So in this case, you are applying again a torque. You need to know what is the difference between torque and moment, okay? So engine torque, supposing this is a motor, and as you know, when the motor is running, this axis is rotating, right? So this torque, this engine torque, the mechanical action generated by this axis of a motor, this axis of the motor, does not produce any force, but only torsion. So in this case also, we will have this like a torque. The example number 6 is same as this one, okay? If you have this tool also and this screw, you want to screw, so you are using rotation, okay? The force you are applying, for example, pushing to maintain this tool, is not generating any moment around this rotation axis, okay? Because the force you are using to push, that force is in the same direction with the axis of rotation, right? Same direction. So it doesn't have, the distance is 0 between this force and the axis. Same axis. The axis of rotation and the axis of force you are using to press. So what we need to, what is our interest here is the rotation, okay? So here you will have a torque again, another torque, okay? This was example number 6. Now we are going for modelization, how to make modeling of mechanical actions. Because we know now there are two big families of mechanical actions: forces and moment, right? And we have seen few examples of those. So now, how can we represent these mechanical actions? How can we do the modeling of these mechanical actions? This is what we are going to see in this part. So these mechanical actions are modeled by vector. So a vector, because they have almost same properties, okay? Application point, direction, and distance, and the norm, okay? So for the forces, in case of forces, how do we represent them? We just use a simple arrow, okay? Like this. This arrow is representing our forces. One simple arrow. In the case, these forces are expressed in Newton. Okay, of course, you can have forces in kilonewton, meganewton, but the international unit is in Newton. You can convert it if you want. So here is example. Okay, we have this one or this representation, which is read like force, the force acting at the point A and exert by the solid 1 on the solid 2. This is representation, or you do this. Means the application, the point of application of the force is the point A. And this is the force applied by solid 1 on the solid 2. In case of moment, how do we represent this? Sometimes we represent moment as double arrow. So it will be same like this, but instead of one single arrow, we do double. You can see this here, one here, and another one here, double arrow. That means also moment. Okay. And this is, and the moment is in Newton meters. Newton meter. So here we have a representation. You see, first arrow and the second one. That means a moment. Okay. If you see this, it means moment, which the moment compared with point A of the force exert at A, the point B, okay? Moment at point B and the force exert at point A by solid 1 on solid 2. Anyway, the most important thing here is the representation, okay? So mechanical action also are classified in, in two families, two big families, okay? For both force and moment, we can also, for the classification, we can use two big families of classification of moment or and forces. So mechanical action are classified in two families. So remote mechanical action, this means no contact at all. So these mechanical actions are acting without touching, okay? Acting without touching. An example is gravity, the weight, action of gravity, weight. So when you see this car, for example, the gravity is acting on this car, but only using the weight of this car. There is no contact at all. There is no contact. And this action is always applied at the center of the gravity, because it is important for you to know where to apply a force. Even if you know how to find the force, how to calculate the intensity, if you don't know where to apply the application, it's not good at all. So you have to know that for the weight, P is applied always at the center of gravity, and the direction is always the vertical, okay? And it is always downward, okay? That is for in case of weight. Another type, okay, the weight P here is in Newton. If you have your mass in kilogram and applying this constant of gravity, 9.81. Some people take it 10, but I think 9.81 is the most appropriate value for this. And so the action of gravity is one example of non-touching, non-contact force, remote mechanical actions. Okay. Another example is magnetism, action due to the magnetism. Okay. If you have two magnets, they can like attract each other, or it can be repulsive actions. So this, if you have the south pole and north pole of this magnet, two magnets, okay, there is attraction between these two. You can see this force. This is force of the magnet number 1 on the magnet number 2. So this action, of course, depend on the relative distance and the relative orientation of these two magnets, right? This is just a class of physics in high school physics, okay? So in electric motor also, we have this kind of magnet. You can see here, south pole, north. These are magnet, south, north, okay? And we have this kind of remote force, remote mechanical actions. We have this kind of mechanical action. The bobbin, I'm not sure if the English name this is bobbin, but when you have the iron, the core, and around this you have a electric wires, and if electricity pass this, it is also acting like a magnet. And you have here a iron, this plate, and there is mechanical action using magnetism again. So for remote mechanical action, we have two types, two examples: action of gravity and action due to magnetism. Okay, this is the first type classification, because we are here classification of mechanical actions. So the first family, non-touching, remotely mechanical action, remote mechanical action. Okay, the second type is, of course, mechanical actions with contact. Okay, in that case, there is contact. So anytime there is contact between two objects, there is a mechanical action. Even if there is just touching like this with your hand, you just touch. Because sometimes if you have an object that is very fragile, even by touching the object, you can break it. Okay, so that means even by touching, you are applying a mechanical action. So anytime that there is anywhere that there is a contact between two objects, there is a mechanical action, always. So any contact causes mechanical actions. Let's say, take this example. For example, we have this small ball and this big one in contact of this wall. If we consider only this big one, we have 3 contact, and each contact will cause mechanical actions. Okay, this contact between this wall is causing this force, this mechanical action. The contact to this between this ball and this wall will cause this mechanical action. And the contact between the small one and big one here will cause this action. Okay. anytime there is contact, there is an action. So this contact action are classified in three categories depending on the form, on the type of contact. Okay, so we are going to give a few examples in each case. Three type of contact. Okay, each type of contact will produce different type of force. Okay, so let's go for the first type of contact, punctual contact, punctual action. That means the contact is at one point, one touch, one single point. Okay, very precise point. That one is easy to determine the. Okay, let's take this example. For example, this element number 1, okay, is acting on this element number 2. So this lever and the cylinder here, as you can see, this will pushing pressure. The element number 1 is pushing on this element number 2. So we can represent this, the force here, okay, on this cylinder. The point of contact is just one point, okay, one very single point here. So it's pushing down here. This is, we call this, okay, punctual action. Okay, so for punctual action, we have three. Remember, we have three types of contact. The first one is punctual one. The second one, we will see here, action distributed on a line. This means you have a punctual contact, many punctual contact along a line. Okay, so here we have example, two elements. This element and this element, this cylinder, this box and this cylinder. Okay, and we can represent it like this. In this, depending that in this view, we have this cylinder here and we have this box. So the point of contact is just like a line. It is not a point actually, it is a line. So it means different, many point of contact following this line. Okay, so it will be something like this, as you can see on the cylinder. So this acting on the cylinder, it will be like this. Each force, like several punctual actions in this punctual actions following this line. Okay, so in that case, if we want to represent this, because we want to make modelization of these mechanical actions, if you want to represent this as one single action, what should you do? So you can do that, saying that all this can be represented in one force, and this force, representative force, is acting on the middle, at the middle of this element, right? The middle of this element. And how do you got this force? You just take this elementary force, this punctual force, multiply by the distance L. Okay, it will be like F. Q is this element, multiply by this length L. Okay, this is second type. Okay, number 2, following a line. Number 3, action, like now, instead of line, it will be on the surface. So it will be like pressure. Okay, this is the third type of mechanical action with contact. Okay, we have remote mechanical action with contact, mechanical action. And this contact, we have three types of contact: punctual, following line, following uh, distributed over a surface. Okay, so here is an example. Let's take example of fluid under pressure. Okay, so this fluid, for example, if you do pressure, applying pressure, we have this like this piston. Okay, like this surface, if we take this surface, we will have several points of contact. It's like all the points of on this surface are covered with contact point, punctual actions. Okay, so if you want to have the force in this case, you have to do pressure multiplied by the surface, right? So we can represent this like this. All the small punctual actions, okay, representative P, P, and we can represent this with only one action, one force. That force will be acting at the center of the pressure, okay, or one single action located at the center of the pressure, okay? So F, pressure multiplied by the surface, okay? The same, another example, when you have braking system of this kind of braking system, you have a cylinder here, and these two elements are like pushing, okay, to make, to brake. Here it's same. In this is like clamp, okay? These two are grabbing this element, right? So if we want, okay, the pressure is around this surface, it is cylinder. So we can just take the pressure divided by the surface to get representative forces this way and this way. Here also it's same. We have these forces here and here acting on this element, disk, and this pressure divided, multiplied by the surface, sorry, we can get representative force like this. Okay, yeah, that's all for this. So we are going to stop here. And this is just the first part of this chapter number 2. And we hope to continue next time. Okay, thank you very much for your time, and see you soon.